In this third and final part of the lecture, we're going to be talking about world models, which is part of model-based reinforcement learning. In the last part, we looked at ACTOR-CRITIC methods. You can see ACTOR-CRITIC methods as modeling an actor, which models actions, and it has a policy neural network that models the distribution of these actions. It also has a neural network that models rewards, which is the value function, the critic, and the baseline within the ACTOR-CRITIC algorithm. But what about modeling the environment? We have not seen any method that actually models the environment as well. So we've seen ACTOR-CRITIC that does modeling actions and modeling rewards. And now we're going to look at how can we model the environment as well. This is part of the world models research line. Here we are going to use neural networks to model the environment. So basically, this is like finding a good representation of where we are currently at. So if we look at this cyclist, he might be thinking, this is an abstract representation of what I'm currently doing. And using this abstract representation, he can use this to act in a more reasonable manner, and he doesn't have to consider every little detail of what's going on in his decision making. So the goal of world models is to find good representations of the current state that we are in, which is especially important for images, which are very high dimensional. So we really want to compress that to a more useful representation. World models can also be seen as model-based reinforcement learning that use neural networks. So model-based reinforcement is basically we model the transition dynamics of the environment, and this then uses neural networks for this. So how are we going to do this? We're going to be using a generative model, a deep generative model, and we're going to learn three different things. We're first going to learn how to represent states, so to get a nice representation of what it looks like. Second, we're going to try to figure out what happens if you actually take an action within that state. Can we predict what happens next? So basically, can we predict into the future what's going to happen when you execute an action? And third, what reward do we receive in what state? To note that this is different from the value function, because the value function is a reward to go. So it includes also the rewards that we receive after taking the action and after this current state up until the end of the trajectory. But in this case, we just model the single reward we receive in that state. World models are also very interesting because it combines a lot of ideas within its course. So the world model itself is a deep generative model. So that's something that we have been talking about a lot in the last couple of weeks. In particular, we're going to be looking at variational AUTO-ENCODERs, which was also discussed in these lectures. They're going to be trained. We're going to be using ACTOR-CRITIC to train policy. We're going to be looking a bit more into detail on gradient estimation methods that can be used within world models. So world models consist of roughly 4 parts. It depends a bit on the implementation, but this is a pretty standard way to think about it. So the first one is modeling the reward that we get in a state. That's a reward model. The second is a transition model. So from a state, what happens if we move to the next state? And the third and the fourth are the state encoder and decoder, which is basically a variational AUTO-ENCODER. Let's start with that. Note that we are not modeling actions. Those come from the outside, for example, using a policy neural network that chooses what actions to take, or some external input, but in this case we are not modeling what actions are being taken. So we use a variational AUTO-ENCODER to find state representations. We have a state, like an image. This is almost a kind of like Doom-like game. We encode this using the encoder neural network of the variational AUTO-ENCODER, and then we get a state representation, low dimensional state representation, which is just a vector that represents the state. We're going to call this Z. So it's like the Z is going to be the low dimensional latent state representation. Like in other VAEs, we'll decode it and try to reconstruct the state again. In the World Models 2018 paper, this is done to try to reconstruct, to reconstruct the frames of the screen. And as you can see, it does fairly well to reconstruct these, but if you take a very good state-of-the-art variational autoencoder, you're probably going to get even better state reconstructions than this. This is one of the first experiments that really try to do world models with VAEs, but I think nowadays we can get even better reconstruction on our VAEs. So how are we going to train this VAE? It's actually not that hard. What we're going to do is we're going to simply collect some experience by acting in the environment. So we are basically running our agent within a real environment, and then we collect some experience. So we collect states, acting, reward states, transitions, and we keep all this experience within a training data set, and use a training data set to train our variational autoencoder to reconstruct these states. So it's a really easy way, it's a really easy loop. Just collect experience in the real world, add it to the training data, and use it to learn it, to train our VAE. The goal, of course, is to find useful representations of states. This is a bit hard to define though, because what is really useful in this case? You could say that useful representations are representations that really allow our agent to act in the world very easily, so that it can get high rewards. So we should really compress it to the fundamentals so that our agent can act well. So isn't a variational autoencoder a good one? Because a variational autoencoder actually has to store a lot about the state. It has to store everything about the state that it is able to reconstruct the image. So maybe it actually needs to store a lot of detail that it doesn't really need to store for the agent to act well. This is one of the discussion points within world models. How do we represent states? Right now we choose to do variational autoencoders because that's what we know best, and that's what a lot of papers have been trying to do. But it doesn't necessarily lead to a state representation that works best for getting an agent to act really well in the world. Now let's look at the other two components of the world model. Those two components are the reward model and the transition model. The reward model models the reward we get in a state, and the transition model models the state transition from one state to another. Note though that we are not dealing with the original state S, but with the state representation Z. So these models act on the state representations and not on the original states. So they don't act on images. So how does this work in practice? Let's say we have some state representation Z in the previous state. In this state, we choose an action. Let's just say that our agent does this to choose an action. Then we use a neural network to compute our transition model. This is, for example, a neural network that outputs in the final layer a Gaussian distribution, just like the encoder of the variational autoencoder also outputs a Gaussian distribution. So now we use our neural network that models a transition model, which would just be a manipulated perceptron, because our input is also just a sequence of numbers, so there is no need to do a convolution here. Then we can actually sample the next state from this transition model, which just takes in the previous state representation and the previous action. So we use it to sample a new state representation. From this new state representation, which just looks a bit different, but is still in the same low-dimensional space, we can use our reward model, which is also a neural network, to now compute a distribution of rewards and sample from it as well. So now we can also use a neural network to predict what reward is going to be achieved in this state. And then we just repeat what happens before. So we take an action in this latent state. We compute again using the same transition model, a new distribution over new next states, set t plus 1. We sample and we continue. So this is basically the loop. We, instead of using the actual state transition dynamics of the real MDP, what we do is that we use our neural network to predict what state is going to come next. So we just looked at the two models, the reward model and transition model. How do we train these? Like with the variational AUTO-ENCODER, we start by collecting experience by acting in the environment. And we collect all this experience within a training set, and that's it. Next, we loop over these tuples within our experience. So we look at states, actions, and then the following reward and the following state. And all of this we've just saved within our environment, so we can just retrieve it from our training data, essentially. So what we do is we encode the state and the next state using our VAE encoder, so that we get two new state representations. We do this by sampling from the environment. So we take a sample, because this is a distribution and not a deterministic neural network. So we sample from these to get a state representation for both the current state and the next state. We then train our transition model. The transition model should basically predict this next state representation from the current state representation. So from this state representation, we took an action and we got in the next state representation. So what we do to train a transition model is to maximize the probability that of this transition, of this latent state transition. And similarly, from this latent state in the state representation in the next state, we should have retrieved this reward. So we can also train our reward model this way. Now, what's actually very exciting about world models is that we can dream trajectories. This is more formally called latent imagination. And what we can do with this, and this is actually why world models are so useful, is that we can train our agents without ever interacting with the environment. So why do we not want to interact with the environment? It can be very costly to interact with the environment. This can be because the environment takes a long time to run, there's to simulate a lot of stuff, or because there is like a real world cost. For example, if you have a robot that acts in the environment, this robot can break or it can take very long to run. So if you can just dream up what should happen in the world, then we can actually train our agent by trying to optimize what happens within this dream. And this is actually pretty exciting stuff. So let's see how that happens. So in this video, we actually see a trained world model that's dreaming up a sequence of states. So it's actually completely able to do this, right? So this just looks like kind of like the game. It looks very fuzzy a bit, and then some weird stuff happens. Some kind of like bullets suddenly jump out or don't come or whatever. So it's a bit buggy, but it does clearly represent the same game. But this is all in simulation. There's actually basically all we did is that we modeled this environment using our neural networks, and then we used generative modeling to sample states and see what comes out of it. So how do we now train our agents using this world model stuff? We're going to train an ACTOR-CRITIC algorithm here. So we choose an initial state, like a real world state, and from that we start. So first what we do is we encode this state using our variational AUTO-ENCODER, and then we're going to loop. First, we're going to choose an action from our policy. Then we're going to transition within our latent space. There's one thing I should notice before I go on, it is that the policy actually now takes on the input Z. So the policy now acts on state representations and not on states themselves. So that we train a policy to work on state representations, which is much more low dimensional and easier to train on than images. So we can actually use a multi-layer perceptron there and not a CNN within our policy. Okay, so we chose a policy, we chose an action. Then we're going to transition. So we chose an action, and then we take in the set representation, transition to the next state representation, sample from it. We do the same for the reward, just as we showed. And then we're just going to do an ACTOR-CRITIC update. Don't look intimidated here. This is exactly the same equation as during ACTOR-CRITIC lecture. But the only difference is that we now use Z instead of S. So we now act on state representations instead of states themselves. And nowhere in this whole loop do we ever interact with the environment itself. So we can completely train our agents within these world models. That's very exciting stuff. So what does a complete training loop look like? First, we start off with a policy. And from this policy, we just start acting in the real environment. That way, we can get some experience for our world model to be trained on. So our world model can really make sure that it is being trained properly and that it looks good, right? Then we train our VAE so that it can reconstruct states properly and we can get good state representations. We train our transition model, so the reward and the transition dynamics. Then finally we train our ACTOR-CRITIC algorithm by dreaming. So then we don't actually interact with the environment and just train it within our dream. And we go on and loop. We should actually loop here. So one downside of this is that we should then, after training the ACTOR-CRITIC algorithm, we should again start interacting with the environment to get new experiences. Because it can happen that our agent really improves and now starts visiting new states that haven't been visited before. And our world model doesn't really know anything about these states yet because we haven't seen them yet. So therefore, after our agent improves, we should again start interacting with the environment so we can get new information on the new states that we might visit. So next, I'll walk you through how this computation works. We start off from some real state, S0, which is a real actual image. We encode it using the encoder network from the VAE to get a state representation Z0. From the state representation, we can compute the probability of actions or the policy and sample an action from it, just like we would in reinforce. We also use a state representation to compute the value function and estimate the value of that state. We use the action in the state representation to compute the transition dynamics over latent state representations and sample a new state representation Z1. We use this both to compute a sample from the reward. So we sample a reward using our reward model, which is also a neural network, and also to estimate the value of that state. And just keep on repeating. So we use a state to predict an action and sample an action, and then again compute the transition dynamics for the next state. There's one very exciting part about this. Recall on the last lecture when we discussed reparameterization in the gradient estimation part of the lecture. We discussed that we cannot use reparameterization within reinforcement learning. So why was this? The reason was that we can reparameterize samples from the policy distribution like over here. However, that doesn't really solve much because the environment is still a non-differentiable computation. So this still all is non-differentiable, however we manipulate it. We still cannot actually get a differentiable path from our rewards or our value function to the parameters theta. So reparameterization didn't really solve anything there. But that's not the case within dreams, because we actually do have a differentiable environment now, because our environment is now actually a neural network as well, namely this neural network over here. So what if we reparameterize everything here? let's actually do that. So here we reparameterize, here we reparameterize, here we did. So to note it a little bit better, these are the steps that we reparameterized. And that really solved a lot of the non-differentiability of this problem. In fact, if you look now from the value function, we can actually move all the way back to our parameters theta. So we now have a path to our parameters, which are within our computation of the probability distribution over actions, our policy. So why is this? Well, we can just simply backpropagate over every sampling step. So we go back, so we compute our value function from the next state representation. We can go back through the last state representation, through the sampling, so through that reparameterization over here, through the transition dynamics, through the sampling over the actions, all the way into our policy network. So we can actually backpropagate through our dream to efficiently train our actor with very low variance. And this is actually a very simple modification of our algorithm. So we start off exactly the same. We start off with initial state, and we sample an action, and we also sample the next state using the state transition over state representations. The only difference is now is that we reparameterize these samples instead of using a normal sample. We train the critic exactly as we did. Now the only difference is that we, instead of using this policy gradient-like update that reinforces this log policy probability, now all we do to train our actor parameters is that we directly find the gradient with respect to our policy parameters of the value function. So basically saying we want to maximize with respect to our parameters the value function, but and only with respect to the policy parameters. So basically, what policy maximizes the output value of the value function. So we do a complete backprop through our dream to train our actor. This is actually a really good method and really sample efficient. This is used within the Dreamer network, which is a very cool DeepMind paper of published in iClear 2019. You can see that it has learned pretty convincing behavior. And this is completely trained within our dream. You can also see the differences between this is the real world, the first line, and this is the world actually trained within the dream. And the transition dynamics are completely within the dream. So even though this is a very complicated control task on images, it's able to reproduce it very, very clearly. It really looks like it's barely a significant difference between the two. And even also if you look at the really pixel differences between the different images, you see it's actually not that big, especially not for some of them. So it is a really efficient method to really train agents very simple efficiently. So to wrap up, world models keep a model of the environment. And this is very useful because we can train our agents using world models to really increase the sample efficiency of our algorithms. The world model consists of two parts: a variational AUTO-ENCODER that represents states, and a transition model that represents the dynamics. We can train an agent without any interaction with the environment, but we still have to collect some experiences within the real world to train our world model. The cool thing is that we can backpropagate through our dreams, through our trajectories sampled by the world model to efficiently train our actor. This was the last part of the deep reinforcement learning lectures. I hope you enjoyed them. Let me know if you have any questions.